Hey, welcome back to Math with Patrick. Today is May 24th, and we are solving problem number 144 from the Daily Epsilon calendar. And we need to show why this x value right here is equal to 24 today. So it looks like we have some kind of information about the variable y, and then when we plug it in here and do this exponentiation, we should get 24. So let's, I guess, kind of unpack it a little bit. Maybe it'd be nice to solve for y. So I know that anytime we have some kind of exponential equation, we can always rewrite it with logarithms. And I think that I'm going to write this as log base 12 of y is equal to 18. One way that I just kind of remember it visually is that this is my base, that is my exponent, and then that's my answer. I just did this wrong. Glad I checked. 12 is my base. 18 is the... is this right? Yeah, okay. 18 is like the answer, and then y is the exponent. Because with logarithms, you solve for the exponent. There we go. So this is 12 to the power of y is equal to 18. Okay. And then somehow I need to plug that into the second equation, but I don't really like how in the second equation I have y in two spots, right? Like I have this y in the numerator and I have this y in the denominator. And I think it'd be simpler if I figure out a way to just have one y, because this is a pretty hard number to work with, and I'd rather only work with it once instead of twice. Fortunately, there is a way to rewrite these kind of rational expressions. I have a fun trick that I like to use. So here I am going to, what am I going to do? I would like to split up this minus 5 as minus 2 and then minus 3. And so I'm still going to keep my denominator the same. So I still have y minus 5 on top and y minus 2 on bottom. But here you can kind of distribute this denominator. And so we're going to get a y minus 2 over a y minus 2 on the left, and then minus 3 over y minus 2 on the right. And that y minus 2 over y minus 2 is just the number 1. I mean, maybe I should be careful, and if y is equal to 2, then I'd actually be in some trouble here. But I also know that 12 squared is definitely not 18, so I'm not in any trouble. Okay, so that was a 1 minus, and then 3 over y minus 2. And then finally, I don't really like having this minus here. I think it'd be a bit more useful if I call it 2 to the power of 1 plus 3 over 2 minus y. So I'm doing two things here. Thing one is that if you flip the terms in a difference or like a subtraction, all you really do is negate it. So these two things are basically equal as long as I stick a negative sign on it. And then thing two is I'm taking this newly produced negative sign and kind of multiplying it into this negative. And so a negative times a negative gives me a positive. And then finally, if I have 2 to the power of two numbers where they're added here, I can use an exponent rule where I can split up this sum into two different exponents, because it's essentially I have some amount of 2's here and then I'm multiplying some other amount of 2's there. So of course I should have a plus b amount of 2's all being multiplied. And ultimately this means x is going to be equal to 2 times, well, I guess 2 to the power of 1 times 2 to the power of 3 over 2 minus y. That's kind of the reason why I decided to remove that negative sign, just because I didn't want it kind of lingering over here. Negative exponents are not really fun. Okay, so, well, x is supposed to be 24 today, and I really don't know how to solve this problem without just kind of like putting this assumption in there. And so I'm going to put a little question mark equals here. So I'd really like to show that this is true. And currently I don't really know that it is. But if this is true, that must mean that 2 to the power of 3 over 2 minus y is equal to 12. So I'm kind of like taking this hypothesis along and seeing what happens if I claim that this is true. So let's unravel this and then solve for y. I have another exponential equation. I can rewrite it with logarithms. I think I'll do it right this time. It's going to be log base 2, and then 2 to the power of, so the power goes over here, and then the 12 goes back here. So this logarithm equation I can rewrite as 2 to the power of this exponent is equal to 12. That's what I had before. And then I can do some algebra steps to reshuffle this stuff and isolate y. One algebra trick that I like doing is that any time that I have an expression is equal to a fraction, you can just swap these two. The steps involved in this is, there's just two. I'll just kind of show it with some letters here. I'm allowed to multiply both sides by that c, so I can say that c times a is b. And then I'm allowed to divide both sides by the a, so I have c is equal to b over a. And if we compare that to what I started out with, all I really did is just swap the locations of the c and the a. And so that's what I'm going to do here. I'll just swap the locations of my denominator, so I'll put it over here, 2 minus y, and this part on the left side of the equation, so 3 over log base 2 of 12. All right, I guess I should isolate y. So I'll subtract a 2 from both sides. And then, oh, you know what? I guess I don't like having the negative y, so ultimately y is going to be equal to 2 minus 3 over log base 2 of 12. I'm doing the same thing from earlier where like negating something is the same as just swapping the two terms. So this is equal to y according to this kind of hypothesis. Like, I'm not quite sure, right? I don't really know that y is equal to this, but that's what this kind of assumption is creating. We also know, though, that y is equal to log base 12 of 18. And so if this is true, if this is actually equal to log base 12 of 18, then everything is consistent. Of course, I can't look at this and know that these are equal. I have no clue, right? Right now I can't. But I think we can run through one more set of logarithms and algebra steps to kind of show that these two expressions are actually the same number. Okay, so I notice that here I have just one thing, and here I have two, right? I have this, and then I have that. I have two terms here. And usually when this is the case, finding a common denominator is a good idea. So I could try to find some kind of common denominator of log base 2 of 12. Maybe I need to change around what that 2 looks like. I'll just put the same denominator here, log base 2 of 12, but I still need this whole thing to have a value of 2. So I need this thing on top to be twice the value of the bottom. So something like this totally works. And then why not? Let's use a little log rule and actually put that multiplier of 2 into the argument. That'll change that 12 into a 144. And, well, if everything is a logarithm, why not change that 3 to another logarithm? Log base 2 of 8 is the same as 3, because 2 to the power of 3 gives me 8. All right. Actually, I don't know that this is true. This is still a little question mark. Let's just rewrite the right side of the equation. I will kind of shove my denominators together because that's the common denominator. And then anytime that you have a difference of logs, you're allowed to write it as the log of a quotient. So it's going to be 144 over, I was going to write 18, just over 8. And, that's log base 2. And then finally, well, not actually finally, maybe 2 steps away. If we do this 144 divided by 8, why not? Let's just long division that real quick. It will go in 18 times. So I can say log base 2 of 18 over log base 2 of 12. And then now, to me, I actually do know that these are equal. There is a change of base rule where if you have some kind of logarithm like this, you're allowed to write it as log of the top one. So I guess I'll just do 18. Log of the top divided by log of the base. So these two things are equal to each other. And the cool thing about the change of base rule, kind of in the name there, you can change the base. The base could be whatever you want. This base could be 10. It could be 5. It could be e for the natural log. Here in particular, I want it to be 2 because then it matches my expression on the left side. So using what I know about the change of base rule, I know that this is equal. And if we work our way up through the logic, what does this last expression tell us? Well, it tells us that this is equal, so this is good. It tells us that this is equal. It tells us that these are equal to each other. So it tells me that this is the same value for y. So it does tell me that these two things are the same. So when I plug in my actual value for y, y is equal to this, according to the first equation here, and I showed that these two things are equal, so y is also equal to that expression. So it means I'm allowed to do all of these algebra steps and reshuffle it this way. And then so now I know that this indeed is equal to 12. And then finally, I can substitute that 12 right back in here. And that does confirm that x is equal to 2 times 12, or 24. What a ridiculous problem. I don't really have a good way of solving this forward. Like you saw how I went all the way down and all the way back up. I would really like to be able to not assume that x is 24, but I really wasn't able to find another good way to work through all the logarithms and exponents and algebra. So if you come across a good solution, please let me know. I would love to have one that's more efficient than this, but this is the best that I was able to come up with for today. So what a monster problem. We can confirm, though, that x is 24, and I will stop yapping. All right. I'll see you tomorrow. Bye-bye.